Thank you. All right. Welcome everybody to the fall 2017 Colloquium series. As you might know me, I'm Dick Schmer, the professor in charge of the Colloquium series here. We get to start off our series this year with a great talk by Barbara Cohen, who's coming over from NASA Goddard. She's joined me back in February from Marshall Space Flight Center, and now is part of 698, the Planetary Geodynamics Laboratory.
Geology, geophysics, and geochemistry.
Okay, yes.
So a little of everything.
The shifting of the interest. But Barb's very interested in sample science. She's looking at the geochronology and the geochemistry of meteorites and rocks from Mars, from Earth as well, the meteorites, and thinking about the moon as well. So today she's going to be talking to us about the violent early solar system. So we'll get an overview of what's going on in the earliest part of our solar system, and then looking at the samples that give us information on that. So let's please give Barb a very warm welcome. And
thank you. Thank you for having me, everyone, and thanks for all the meetings today. It's been really nice getting to know some of you. I'm really excited to be here at NASA Goddard. I came from NASA Marshall, as Nick said, and there we didn't have a great university to partner with. So part of this talk is a little bit of advertisement about me and what we're doing in my lab, and trying to get you guys interested and maybe pass the word around if you want to come work in my lab or do some projects together. That would be really great. And if you have questions, just interrupt me. Raise your hand or just yell them out. And especially if I slip into jargon that you don't understand, just let me know. One thing I want to put as a disclaimer, I talk about the early solar system. There are people who talk about much earlier times than me, 4.5 billion years ago, and depending on how many significant figures you want to put on that. But we also get trouble if I say the late heavy bombardment, because it's not really that late. So the area that we're talking about here is about 4 billion years ago. It's about 500 million years after the formation of the solar system and the Earth-Moon system. So it's neither early nor late, and I'll probably use those words interchangeably, but they're all referring to that same period of time, about 500 million years after the solar system formed. I'm not probably up to the task of convincing you that geochronology is awesome, but geochronology is awesome. Sometimes, people just think we're in the rock lab and we're getting ages of rocks and we're getting dates of rocks, and isn't that nice, and we can all just go away and be in our cave. But geochronology is more than just rock ages. A lot of times when we have press releases in planetary science, especially for Mars or the moon, we want to know when something happened. Geochronology is what puts those in order. When we get a rock and we know that it's been abraded and it's been in a dune, when was that dune active? When was the wind active on that planet? When we have something that's got aqueous alteration, when was that water active? And how long was that water active? That's a really important point, especially for astrobiology. If it's a transient cold event, that's much less exciting for astrobiology than a big hydrothermal system that's been set up by maybe a large impact for many, many years with nice warm water. So what are the constraints on the time evolution of the dynamic solar system? That's what we're really going to focus on in this talk, but these are all also important. When was Mars warm and wet? That's every press conference that we ever have about Mars. The first question is, when did that happen? We don't know. It would be really nice to know some of these with some real absolute ages. How much time did they have? How long were planetary heat engines active? If you're interested in volcanology, especially across all of the terrestrial planets, how long were these heat engines active? What kept them active? And then how long were current surfaces exposed to space? Another astrobiologically relevant question for how long things can sit on the surface while they're being bombarded by UV radiation or cosmic ray radiation. So all these are geochronology questions. And I'm interested in all of them, but we're just going to talk about the first one today. So this is my fave astro plot on Twitter, if you look it up. It made it into the top 5 because it's such a powerful plot. What we have is the cumulative number of craters on the moon, greater than 4 kilometers, but you can pick your cutoff here, and time before present. So this is an absolute age, and this is a relative age. And this is the only place, the moon is the only place where we're able to make this correlation. And it's because we had Apollo astronauts who went to well-dated, crater-counted surfaces, picked up that rock and brought it home, and we could date it in our laboratories and get an absolute age that we could correlate with this relative age used by crater counting, right? So we can do crater counting on every solar system body. We do crater counting on every solar system body, but we don't have an absolute age to back that up. And so what we do is we take this curve that we have for the moon and we apply it with various fudge factors to other planets, to every other planet, to Mercury, to Mars, to the outer solar system satellites, to Pluto, with varying results of accuracy or precision. What we'd really like to know is how do we make this curve for those very different dynamic environments? What does it look like for those? The other thing that's relevant about this plot is this dashed line here. So this dashed line is a constant production rate. If you take a production rate for craters, right, so, or for the impact flux is really what's relevant, the size frequency distribution of things hitting the moon, by extension hitting the Earth, and just extrapolate it back through these points and extrapolate it back here, we get a pretty good fit for these young craters. We get a reasonable fit for these. These are all Mare basalt surfaces, nice crater counts, really precise radiometric ages. But you can see here is when about 4 billion years ago is when that nice model diverges from the data pretty significantly. And that is something that we've been trying to investigate ever since we figured this out for the moon. And so these are all surfaces. They're not, they're highland surfaces. They're all just regolith. So we can count craters in them, but we don't really have a time zero for those surfaces like you do with a nice basalt flow. So those are our best guesses, but you can see they're more intensely cratered than we would expect given a constant production rate. So either the production rate changed or something's fundamentally wrong with our understanding of how craters form and are retained on surfaces. And what I'm going to argue to you is that the production function did change in the past, and what we see now is not what we saw in the past, that there was a significant change in the production function.
Can I ask?
Yes?
What I see in front of me are a large variation in the shapes of the gray zone, which I assume reflects the uncertainty.
Yeah.
Why?
Probably with the lava flows, because not everything forms at the same time, or we dated them with different radiometric systems. So ideally what you would do is you would take one rock, you'd date it with every radiometric system, you'd look at the closure temperature for every radiometric system, and you'd get a nice cooling history of that rock. It's not always possible to do. And also some of these Mare basalts are made out of multiple flows. Radar is finding that now. So Gareth Morgan at Smithsonian has been doing some of this work, other people have, where there's multiple overlapping flows. And they may be from the same source, and so they may be geochemically pretty much identical to each other, but have differences in age. And we wouldn't be able to tell that if we just picked up a scoop sample or got it from a thrown sample. We would not know that it came from one lava flow or the other. So there may be geologic differences. It may also be inter-laboratory calibration. It may be different radiometric systems. It could be all of those together. Anyone else? Right. Okay, so when we first started out looking at the moon or looking at any planet, this is how we thought we could relate samples to the impact flux. So what I'm going to be talking about in this talk are not just sample ages, but ages that were reset by an impact event. So we're mostly talking about potassium argon. There are some other systems that also record this. Potassium argon is a nice one because argon is a noble gas, and so it's easily diffused by a heating process. So you don't have to totally melt and recrystallize the sample to lose argon, which is losing your daughter, and resetting your time clock back to the age of the impact. So we like this system for impacts. And if you're interested in impacts, we use a lot of potassium argon. It's not a perfect system, and I won't go into all the complexities of it, but largely that's what we're talking about. And if you were looking at things that were just reset by impacts, you might expect very naively that in time zero, 4.5 billion years ago, when the Earth and the Moon formed, there was a lot of dynamics going around in the solar system. Everything was being formed, lots of protoplanetesimals, everything's whizzing around, colliding with each other. You have a lot of impacts. That means you create a lot of samples that would lose argon and would be reset at that time of impact. So you'd have a lot of samples on the surface that would sort of reflect that time of impact. And then as the solar system settles down, everything gets into a nice Keplerian orbit, you don't have a lot of collisions anymore, and so the number of impact-affected samples would decline with time. So if you could get a perfect sampling of the lunar surface of all the rocks, and then you looked at the ones that were affected by impact, and you stacked them up on a histogram, you might expect it to look like this, with some curve of your choice. If that were true, and that was what we found on the moon, I wouldn't probably be here talking about this, because of course that's not what we found. So for the Apollo samples, and this is in a compilation that Don Boggart made in 1995, what we see instead of this nice declining flux is we see a pile up of samples right here at around 3.9 billion years. The salient points here are not a lot is happening out here, but more importantly, not a lot is happening in here. And this is where you would expect, this is your greatest mismatch. This is where you'd expect a lot of samples to be, and we don't see hardly any. So that's a huge mismatch. The way this was interpreted was that there was a large metamorphic event on the moon, probably related to impacts. A large flux of impactors came in, metamorphosed the crust of the moon at this time, and so everything that maybe had these ages was reset at this time. It was called the lunar cataclysm. You see this not only in argon, but you see it in uranium. That was the first one. Uranium-lead was the first actual system to show this. It's got a concordia, the crystallization age of the rocks, at 4.5 billion years. It's got a discordia age, the age of the metamorphosis, 3.9 billion years. So they record, uranium-lead is nice, it records the time of crystallization and the time of disturbance. And so that's what this was. And then you see this borne out in argon and in rubidium-strontium as well. So since that result, people have been really going gangbusters trying to look at all the lunar materials they can to try to find whether this is something that's real or not, whether this is something that's an artifact of the samples that we picked up, the samples that we chose to date, the systems that we used, how we focused. So this is a whole compilation of samples. The yellow is since 1995, and what you can see is we've got a lot of samples that populate down here, which is good. These weren't the most interesting samples from the Apollo missions, but they're there, so that's what we would expect. You get a nice decline here and it peters off. Maybe there's something going on in very recent years, maybe not. That's a point of contention right now, whether that is a real effect that we're seeing or whether this is an artifact of sampling. And most people would argue it's an artifact of sampling. So I'm not going to concentrate on that today, although you can ask me about it if you want. But the real point here is, where is this population? So when I came in and did my dissertation, I was looking in lunar meteorites and I was looking for these ages, and I just thought, well, no one's looked in lunar meteorites. That's where they are. I'm going to find these. I'm going to find the 4.2s and the 4.4s, and it's going to be done, and I'll have solved this issue, and I'll be rich and famous. And of course, yeah, you don't see any there, which means I didn't do that.
Are you still rich and famous?
I'm not rich and famous. I missed my boat. So this leads to what we call the classic lunar cataclysm, also synonymous with late heavy bombardment if you talk to dynamicists. They call it late, like I said, because it's about 500 million years after the solar system formed. We call this the cataclysm historically because it was on the moon and it was a single metamorphic event that was caused by a spike of impactors. And so it was called the cataclysm. It resurfaced the whole moon. It created 20 to 40 lunar basins. So when you look up at the moon and you see those big Mare basalt plains, the big circular Mare basalt plains, they're circular because they're filling in basins. Those basins are thousands of kilometers across. They are enormous craters. And because the Earth and the moon function as a single gravitational cross-section to something at infinity, I promise you, every crater you see on the moon had a counterpart on the Earth at some point. So the moon got pummeled, that means the Earth got pummeled. The Earth got pummeled at a critical time in Earth's history. Right here, just before 3.9, this slide is a little bit dated now. This is from one of Dave Kring's web pages, but I like it because it's got the moon hanging over you like gloom and doom. The earliest isotopic evidence of life on Earth, the earliest fossil evidence of life on Earth are around this time. Now, that's not a coincidence because the earliest rocks on Earth are not that much older than this, and the earliest minerals, you can push it out older and older. But there's not a lot of crust on the Earth. There's just not, and it's because we recycle, right? We have plate tectonics, we have erosion, we have a lot of crustal recycling. We know that at this time on the Earth, there was sedimentation. So those rocks are metasediments. So there was sedimentation, there was continental crust, there was wind and atmosphere and water. So it probably looked a lot like it did today in that sense. What happened at this time that there's nothing older than that? Is that just how the Earth works? Or did it get, I won't use an expletive, did it get the heck kicked out of it at this time by this pummeling that the moon took? It's a really provocative question. So this is something that has really wide-ranging effects for the habitability of the Earth, the rise of life on Earth. But Imbrium. Imbrium is this giant lunar basin. It's right here. It's the youngest, well, not the youngest. Oriental is the youngest over here on the side, but Imbrium is the second youngest basin on the moon, and it's one of the biggest basins on the moon, and it dominates the entire near side. Now, this is what the moon looked like when we sent the Apollo missions and the Luna missions from Russia to bring back samples. And so we tried to go places, we tried to go to the Imbrium Basin and look at that. We want to know how old the Imbrium Basin is. We went to some other places. We wanted to get away from basins. These are some different basins. So we went to all these different places, and that was really a good thing to do for geologic diversity. But what we know now, and this was much later, this wasn't until Lunar Prospector in the 90s that we got a global look at the surface of the moon and the surface terrains of the moon. And what we see here is something called the prosolarum creep terrain. And this is largely Imbrium ejecta, but it's also other basin ejectas. When the moon formed and crystallized, it has a crust, a mantle, and a core, like the Earth, like Mars, like all differentiated planets. Something that's maybe unique to the moon is that the crust, when it crystallized, was less dense than the liquid, and so it floated to the surface and made this cumulate plagioclase crust. The mantle materials, your olivine and your pyroxene and those kinds of minerals were more dense than the liquid, and so they settled out. And so you had crystallization both ways of the moon, and what you end up with is a liquid inner layer. And that liquid inner layer captures all of the elements that don't like to go into crystals. So things like uranium and thorium, potassium, rare earth elements, phosphorus, your incompatible elements, they don't go into the crust and they don't go into the mantle, they get sandwiched into this layer, and we call that creep for potassium, rare earth elements, and phosphorus. It's also got all your heat-producing elements, thorium and uranium. So it's a really interesting artifact of the way the moon formed. We don't know if this happened on other planets, but it certainly didn't happen to the extent it happened on the moon. And this got thrown out. So the crust was thin on the near side. It was underplated by this creep material. When you had a big basin, threw this material out and distributed it all over the near side of the moon. And so you can see now the Apollo sites don't look so different from each other. They're all near this prosolarum creep terrain. And when I'm talking about potassium-argon dating, where's your potassium? It's in this creep. That's a really easy rock to date. And so when you're looking for something to date, you're not going to look for something with no potassium because you can't date that. You're going to look for something with potassium. And so a lot of people have argued that Imbrium, or the prosolarum creep terrain, has biased our view of the sample collection, that we're dating Imbrium ejecta over and over and over again. So that's a real viable hypothesis. Let's look at it. Let's look at Apollo 17. That's pretty far away, right? There's Apollo 17. We collected impact melt breccias there. There's two massifs there. It's on the edge of the Serenitatis Basin. We think that the Serenitatis Basin threw out ejecta, made these massifs of Serenitatis ejecta. So we went there to look specifically. That was one of the points of the Apollo 17 mission, was to look for Serenitatis impact melt. So we found this poikilotic impact melt. It's 3.89 billion years old. That is just a slightly bit older than Imbrium at 3.85 billion years, but it seems to be resolvably different. So we think, okay, that's the age of Serenitatis. So Serenitatis formed right before Imbrium, which means that it was part of this huge event called the Cataclysm, right? Right, all done. Not really. Okay, so here's Apollo 17. It's in this valley right here. Here's the North Massif, here's the South Massif. If you go and look at the LRO images, you can actually see the lunar lander. You can see the tracks the astronauts took. Super cool. So these are supposed to be serenitatis. They're overlain by this hummocky terrain called the sculptured hills. The sculptured hills have been traced back to Imbrium. So Imbrium laid down those sculptured hills on top of what we thought were these massifs coming from serenitatis. That's okay. Maybe we don't sample the sculptured hills. Maybe we can go right into the massifs. Deborah Hurwitz-Needham did some really cool work. This is a side-on view of this massif here. This is a side-on view with some LROC pictures, and you can see boulder tracks. So you can see where the boulders came out of. You can see these little green lines are places that look like they're contiguous rocks, like they could be bedrock. And then you see those boulders coming down, and then you see them at the end, and here they are at the end with the lunar rover for scale. So those are what we sampled. So you can trace them back to where they came out of, to something that some people might call outcrop. And you can say, well, that's what we sampled. So, all right, we sampled something that wasn't Imbrium. It's right in the middle of this massif, and it's from bedrock. Done. That's the age. So here's what you get when you date those samples. This is just a histogram. These are just different Apollo-17 poikilotic samples, and this is their age. There's the midline, and that's the precision of the measurement. So here's the Imbrium, just for scale here. And so this paper, tried to argue, and a lot of other people tried to argue, that this is the age of Crisium and this is the age of serenitatis because that's what these samples show you. But if you didn't know that's what they were going for, would you think that's two different ages? It doesn't look like it. It looks kind of like a mixture between two ages, or maybe even more. You might have something that was reset down here and is incorporating orbital material to some degree. You might have something that formed up here and was partially lost some gas. You could have any number of explanations for this. This to me is not super convincing. So not to dump on this particular paper because I think it's some very careful work and it's very thought-provoking, but the main point being here is ejecta facies are very poor places to do this kind of investigation. We really don't know how to effectively take a sample from an ejecta blanket and tie it back to its parent basin, especially because those basins are now flooded with with basalt. So we don't know the composition of the original impact melt, so we can't use that to tie the ejecta back to the basin. It's very difficult.
So help me to shake away a bias.
Sure.
The second sample and the second last sample had very small uncertainties.
Up
Can
here?
I just say that the second sample tells me about Crisium and the second last sample tells me about
Maybe. You can't tell by age alone.
And say that the most precise give me the best estimate.
That's possible. If you had perfect sampling and you knew, these came with a name on them that said, hi, I'm serenitatis. Now, there's a paper out too that says that serenitatis is much older than Nectaris because the crater count age is so much higher. The serenitatis impact blanket is very heavily cratered compared to other basins. And so that actually argued that it's older than even the Nectaris. So this is inconsistent with the crater counting age. So the point is that, yeah, this may be the age of something, but we don't know what. We don't know that this is serenitatis. And the other point I wanted to make here is that Imbrium is a really big basin with outsized influence on our sample collection. Personally, I'm not ready to go to the extreme Larry Haskin that he went to and said everything we've ever dated is Imbrium. I think there are resolvable age differences and resolvable geochemistry differences. They're very small. And I don't think they give us the age of some of these big basins reliably. All right, what else can we do on the moon? This is what I worked on, lunar meteorites. Lunar meteorites are feldspathic in composition. They have very little potassium. This made it a really good challenge to give to a young graduate student. Here's something with no potassium. Potassium argon date it. Have fun. So these ages have pretty large uncertainties. What I'm going to show you for the rest of the talk are these ideograms. They're like histograms, but they take into account the uncertainty in a measurement. And so we plot them as individual Gaussians with a width that's comparable to their uncertainty. And then you add them all up just like a normal histogram. So what we're showing is the probability that a sample has this age. So you can read it like a histogram. Higher means more probability that something's got that age. So And also to keep you awake, here's 4.5 on this side and goes down from there. So the lunar meteorites, I thought, oh gosh, they have no potassium. They're not contaminated by Imbrium. They don't come from Imbrium. They come from maybe even the far side of the moon, where it's nice and feldspathic. But again, you can quibble with what this means. I think it means that these are small samples that form in non-basin impacts. But the point is that you have nothing out here. There's just no reliable ages that are old that predate Imbrium. Is there anything else we can look at? Katie Joy did some work about solar wind implantation. The longer a surface has been on the surface, the longer a sample has been on the surface, the more solar wind has been implanted into it, and you can use that as kind of an antiquity index. So she found these samples and tried to say, okay, here's solar wind and here's the age. And so we went and looked at the oldest ones that she could find, and all of those class, 3.9 billion years. They're Apollo 16 samples. It's a very common age to find in Apollo 16. We were hoping it would be older because it had old solar wind, but I guess it was just super retentive to solar wind. There are a lot of other people out there looking at this problem and really trying to take apart Apollo samples, looking at zircons, looking at just anything we can find. And there are some older ages out there. People are trying to find these. There are finding 4.1 is coming up a little more frequently. There's maybe a handful of samples that are 4.1, maybe 4.2. So we are finding these, but they're very small amounts. There's a class here and there. They're not widespread. They're very difficult to find out of this haystack of a lot of other different things. So I'm not saying they don't exist. I'm just saying that it's really going to be hard to use lunar samples to find these old ages. Where else can we look? Let's look at asteroids. If the Earth-Moon system was so unique that this cataclysm only happened on the Earth-Moon system, that would be dynamically improbable. There are very few scenarios that the dynamicists could think of that would bombard the moon and the Earth, but wouldn't touch anywhere else in the solar system. So at this point, the dynamicists are trying to think of, well, what could possibly cause this? And if it was something that's left over from the solar system, we might expect it to affect other planets. So we might expect it to affect asteroids. We have samples from asteroids. We have lots of meteorites from asteroids. The most common class of differentiated asteroids are these HED meteorites. They come from Vesta, which is a very large asteroid, and it's so large that it's differentiated in and of itself, and it has a regolith on top. And that means that it can have impacts that don't destroy the whole body, that would leave a record behind of that impact history of that asteroid. So we looked at HED meteorites, and in particular Howardites, which are regolith breccias. They're very analogous to lunar samples, where it's a breccia. We go in, we find impact melt class that are products of impacts. We don't know which one. We just know that it's an impact-affected rock. We date those. And then this is what we get. So we get a histogram, again, 4.5 billion years out to 2.5 billion years. You get the same kind of buildup that you saw with the lunar meteorites. You get the same kind of drop-off. Oh, but now we're seeing the formation of the solar system. We're seeing that very dynamic time in the solar system where there were a lot of impacts. These are not crystallization ages. People have been very careful to try and say, is this a crystallization age? Is this the formation age? These are impact-affected ages. So this is what we would expect. We would expect to see a lot of things whizzing around, colliding, making a lot of impact-affected things. So it's really good that we see this in these meteorites. So we see this large time of impacts, an increased flux of impacts. We see it go quiet, and we see it come up again. It's super interesting. One of the more interesting things about Vesta, too, is that the relative velocity between asteroids and the asteroid belt, they're all going along together in their little lanes. So, you know, when you're passing a car on the highway, your relative velocity is pretty small compared to the velocity you're going. Same for asteroids. So if one asteroid just collides into the other, it's a very low velocity impact. You can excavate material that way, but you're not going to have enough energy to melt. You're not going to have enough energy to do an impact reset in your sample. So to do an impact resetting in your sample requires impacts of unusual velocity, IOUVs. So that means that there's some dynamical change in population that pumps up the eccentricity or the inclination or something relative to each other that gives you enough energy to make impact melts on that body. The H-chondrite parent body is another one. H-chondrites come from a very large parent body. We think they're related to each other, and there's enough of them that we think we can understand the structure of that body. It's a few hundred kilometers big, or was. And these are the samples that we use. I like this picture. I have been on the Antarctic search for meteorites. I'm going this winter again. And these are the kinds of meteorites that we find with the Antarctic search for meteorites. We call them POSs, or pieces of space. And this is one that's in this study. It's tiny. It's a piece of a howardite, which is an HED, or H-chondrite, which is a very common meteorite. It's an ordinary chondrite. It's tiny. You wouldn't even blink at this. But when you date these, they're pieces of impact melt, and you can make the same kind of histogram you can with the Vesta meteorites, and you see the same salient features. You see this formation of the solar system and a lot of collisions. You see a quiet period. You see it getting pumped up again.
I was just wondering, for something like Vesta or the Moon, wouldn't these ages all be partially reset by the impact that knocks it off the body and brings it to Earth?
Yeah, good question. It can be, but it doesn't have to be. We see that with Martian meteorites, that they get masculinized when they're launched off, but they still show us the original age. One of the reasons we like potassium-argon or argon-argon is you can see both those events, and I'll show you an example later of being able to see both events. In uranium-lead, you can see both events as well, so you can retain a record of both of them. It doesn't get totally reset. It can get totally reset, but it doesn't usually. Okay, Mars, we wish we had more Martian meteorites of more diversity and more lithologies. The Shergottites have been really no help at all for looking at this. They're so young. ALH 84001, which some of you may recognize, it's a very famous meteorite. It does not have life in it, but it does have carbonates, and those carbonates formed at 3.92. And did I not reference you? I'm sorry. Richard did some of this work too. So they formed at 3.92, and that's really a provocative age. That means that there was a hydrothermal system that was set up at 3.92 after the crystallization. The crystallization is very old, and so there was something that set up a hydrothermal system, possibly widespread, possibly very warm, possibly a giant impact that happened around this time to set up this hydrothermal system to deposit these carbonates. That is not the only hypothesis for how they formed. It is just one of many, but it is an allowable hypothesis by this rock. This Martian breccia, Black Beauty, is a really amazing meteorite. It's the first time that we've gotten sort of a regolith breccia from Mars, and I think it has not given up all its secrets yet. I haven't seen anyone publish anything about impact melt lithologies in here, but I bet you there is one or two. This is mostly in the hands of private collectors. That's another reason I like the Antarctic search for meteorites. That's an open collection to everyone. So maybe someday we'll find an impact melt in here that we can look at. On the Earth, just a brief detour into zircons. This is not my field, so I apologize if many of you know more about this than I do, but the point I want to make here is that we've been looking for very ancient zircons, and the zircons form in magmatic systems, but then they can get rimmed and reset, and you can see multiple generations of zircon growth in some of these cathodoluminescence images, and you can go in and get very high resolution spatial dating on these. And so you can date the cores, and the cores, you know, are pretty old. They're magmatic systems in the Earth. But when you date these reset ages or these rimming ages, here's how they pile up. Here's 4.4 billion years, here's 3.8 billion years. And these are zircon ages from multiple research labs. And what you see is this nice pile up. It's slightly older than 3.9. It comes out here at 4 to 4.2. But also these are mostly uranium-lead ages. And uranium is a higher closure temperature system. Commonly, they'll look older than potassium-argon. We haven't fully resolved that for every rock. Again, what you'd really want to do is do them all in the same rock for the same time and build a thermal history, but we don't do that commonly. So uranium-lead commonly turns out to be a little bit older than potassium-argon. But again, the salient point is what's going on out here. There's not a lot of resetting happening on the Earth, even at this time. So the dynamicists really got to work and said, okay, this seems to be something real. It seems to be happening throughout the inner solar system. How can we explain this? Solar system formation is very quick. So the remnants of solar system formation died down. How do we save up some population? We couldn't do that. We couldn't store it somewhere in the asteroid belt and have it go crazy later. So what people started looking at was the migration of giant planets. And this was motivated in part by this work, but in part by the structure of the solar system, our solar system. And then it's motivated even more by the structure of extrasolar systems. So what we see in extraplanetary systems is we see a sun with gas giants right next to it. Now you can't make that by just condensing the solar system, and when you get cold, you get a gas giant. You have to make that far away and drag it in. How do you drag it in? You drag it in by the interaction of other bodies around it, the gas and the dust of the cloud that's forming it, and also the outer solar system bodies. So what you're seeing here is you're looking down on the solar system. This is the sun, and this first planet's orbit is Jupiter. So you're not even seeing the inner solar system here. So you see Jupiter, Saturn, Neptune, and Uranus. So that's important because we start off with Neptune and Uranus reversed from each other from the current system. And then all out here, these green bodies are Kuiper belt objects. So it's similar to the asteroid belt. They're out there. And what you're going to see in this is just one simulation out of many ideas. You're going to see these interact with each other. They're going to get pulled into the solar system. They're going to get passed from Uranus to Neptune to Saturn. And when they get past to Jupiter, Jupiter is so big, it bats them back out. So it prevents them from coming into the inner solar system. But what all that is doing is it's exchanging momentum between these bodies, Jupiter and the outer planets. And what you're going to see is that's going to cause an instability in the giant planets. Uranus and Neptune are going to switch orbits, and you're going to see what happens to these solar system bodies. So this takes a little while. This is one of the knobs you can turn in these dynamical models. Is they're not totally reproducible. They're, you know, if you can get within a few 100 million years, you're doing pretty good. So this takes a while. You can see these getting depleted. You can see them getting passed in, and you can see them getting batted out. And you can see these orbits got much less compact, and they're getting more elliptical, and they're sort of oscillating and wobbling. And then you get out here to 900 million years, and everything goes crazy. Okay, so you get, what you end up reproducing is the structure of our outer solar system. They started compactly, they moved out, these moved in. All of these bodies got knocked in and out, they got knocked through the whole solar system. The other thing that happened is as Jupiter and Saturn move, they sweep resonances through the asteroid belt. So you get asteroids being destabilized as well as the Kuiper belt objects being destabilized. And all of that contributes to bombardment of the entire solar system. So it wasn't just the moon, it wasn't just the Earth-Moon system, it was everywhere, got pummeled at this time in this model. There's other models that show jumping Jupiter and Grand Tack and all of these dynamical models. They were all sort of trying to solve this problem to begin with and then going on to solve the solar system. Yep. Okay, so briefly, what are we going to do next to try to understand this? What we'd like to do is get the age of a basin on the moon and not be fooling around with this ejecta and saying, well, where did this come from? Is this serenitatis or not? How about we go to a basin and we land on the impact melt sheet and we pick it up and we date it? That would be awesome. Let's do that. We could go to the South Pole Aitken Basin on the moon. It's the oldest and deepest basin. It's on the far side of the moon, but it has not been flooded by basalt. There are basalt patches. It has had eruptive volcanism, but it hasn't been totally flooded. And you can see it from orbit. Orbital geochemistry says this is something different. This is the original melt sheet. That melt sheet has probably differentiated in and of itself. It was probably big enough that now it's like an igneous intrusion. But through trace element geochemistry, you can certainly relate those layers together. So let's go pick up something from a basin. Not only is it intact melt sheet from a basin, it's far from Imbrium. In fact, it's antipodal to Imbrium. So there's actually a little tiny bit of Imbrium ejecta that makes its way down and collects right at the antipode, but it's a small amount. It's certainly small compared to that prosolarum creep terrain that we kept sampling over and over again. So there is not a lot of Imbrium ejecta. We also understand what Imbrium ejecta looks like, so we can avoid it. So it is a clean sheet for the far side impact history. You start off with this old basin. We know we haven't contaminated it, so all of the subsequent impacts that happened and reset that melt sheet, we're going to pick up a sample, we're going to get that whole history, and it's not going to be the history of Imbrium over and over again. So that would be awesome. I was a co-investigator on this proposal, Moonrise. It went in to New Frontiers just recently, so keep your fingers crossed. what we would do with those samples is we would bring them back to the Moon Girl lab, which is my laboratory that was set up at Marshall and now is doubled at Goddard because Goddard has this nice helix, multi-collector noble gas mass spectrometer. We have a noblesse. This is moving from Marshall in 2 weeks. I hope it doesn't break. So it'll move and it'll join the helix and we'll have a really, really nice facility. So we mostly do argon-argon. That's my major interest. Iodine xenon is something that we're interested in and we'd like to get set up to do. We can do complete noble gas inventories, cosmic ray exposure ages. We are, Don Bogard shuttered his lab some years ago, and so we took that mantle and said we're the noble gas facility for NASA, but we are committed to collaborating with other people, and that means you. So please consider coming and seeing our lab and seeing what you can do with noble gases or what noble gases can do for you. So I want to show you something that came out of that laboratory recently related to moonrise. It was kind of like a little trial run. There's this meteorite, Dhofar 961, here it is here. It has a lot of thorium in it. Thorium is one of those incompatible elements. It could have come from prosolarum creep terrain, but the thorium wasn't high enough, and the iron and magnesium didn't match either. What it matches is the South Pole Aitken Basin. So here is just a thorium map of the South Pole Aitken Basin, and here are allowable areas that would produce this meteorite. So we're pretty sure we have a source region for this meteorite, and it's right where we want to go with this mission. So how well could we do if we did this mission? So we looked at this impact melt lithology in Dhofar 961. This is an argon-argon relief spectrum, so this is apparent age on this axis. This is the amount of 39 argon released. What we do is we heat the sample incrementally and we measure the ratio at each heating step. And if it were a nice cogenetic closed system behavior, every step would be identical to each other and you would just march across. It's called a plateau. And that's what you see sort of in this region. But you see some, oh, maybe this comes down a little bit, this goes way up, this comes down a little bit. So those are details of the interpretation that tell us the difference between crystallization, subsequent loss. This was done in my lab with very, very small samples. They're about tens of micrograms. When you put 300 micrograms in there, I've never seen argon spectra this good. Now, I designed this lab to be this good, but it's pretty amazing how good this lab is. So this is over 100 steps of a 300 microgram sample. So we can do really well. So when you put all these together, what you find is that you've got a nice mid-temperature plateau here. This is probably your plagioclase and your matrix degassing, and that comes out to 3.532 plus or minus 43 million years, sort of depending on where you cut this off. And this is younger than the uranium lead ages in this row. So the phosphates in this rock were measured with uranium lead, and it's slightly younger. So that's, like I said, pretty common. We haven't resolved that yet, but also there's no phosphates in this particular impact melt lithology that we dated. So it's possible it's slightly different from the ones that contain the phosphates. This rock is a breccia. There's lots of different things in it. So these low temperature steps show that there's some degassing. You can see a hint of it in the more coarse spectra, but you really see this come down. When you extrapolate this down, this is the age of disturbance, so there is some gas loss. There's probably a subsequent impact that caused a little bit of gas loss, but not fully, and that age is down here at about 3 billion years. You have this nice plateau. This is almost certainly recoil. This is a fine-grained lithology with a lot of incompatible elements in it, and we irradiated it for 400 hours. So I'm pretty sure we got some recoil there. Yeah, no. I'm used to working with things that are really poorly behaved, and we have to do a lot of irradiation to do that, and I think this was overkill for this one, but we didn't know. So okay, I think I've convinced you that we need to date all the rocks. So bring all the rocks to me. Let's do sample return from Mars. Let's do samples from every asteroid. Let's go to the moon 15 times, 20 times. Go to every basin. Bring me all the rocks. That would be awesome. That's not going to happen. That's a lot of money, so we're not going to do that. So we want to take our lab and we want to take that to other planets. So in situ dating is something that I'm really, really interested in. This is something that's been going on with me for 5 or 6 years. And I want to take the potassium-argon method to other planets. We actually have tried to do this. The Beagle 2 lander had an explicit aim of doing potassium-argon dating, and it landed. We just never heard from it again. We actually saw the lander. We imaged the lander very recently, and it looks like it's intact. So it did land, but we never heard from it again, so something happened. But Curiosity also is capable of in situ dating. And so I'm going to show you some of these results. It is a difficult measurement to make, and there's a lot of assumptions that go into it. And there's a lot of modeling that goes into it. And one thing that I think is that these uncertainties that you'll see on these ages, there are best estimates based on the measurement techniques, but I don't think they fully encompass all the uncertainties that we have about the rock itself and the assumptions that we're making. So take these with a little bit of a grain of salt. Not huge. These are good. People do really good work on this. So it's not a huge grain of salt, but I think this is underestimating it a little bit. So these are the rocks that we've dated with Curiosity. This is a mudstone, this is another mudstone, and this is a sandstone, this is another mudstone. So they're sedimentary rocks. Sedimentary rocks like mudstones have detrital phases and authigenic phases. Potassium may be moving around. A lot of elements are moving around. So we have, on board we have a XRD, so we can tell what the mineralogy is. We have APXS, which gives us the bulk chemistry. And from that, we try to partition the potassium into its mineral phases. And then we try to understand those mineral phases as they're degassing. So this mudstone, the age you see here is the detrital age. So we tried to make sure that we only looked at the detrital minerals and partition the potassium that way. And you get about 4.2 billion years old. This sandstone was chock full of sanidine, which is great if you're looking for potassium. It's a nice potassium-rich phase. Unfortunately, it's very retentive. It doesn't give its gas up very easily. And the SAM instrument that we have did not fully degas that sanidine. We just couldn't get it hot enough for long enough to diffuse all of that argon out. So it got discordant ages. They don't really tell us much of anything except that rock wasn't a very good rock to do this experiment on. It's no fault of the experiment. Then we looked at another mudstone. This mudstone we did a two-step experiment on. And so the low temperature heating step is jarosite for the most part, maybe some phyllosilicates, so they're the authigenic phase. And then the detrital phase is at the high temperature. And this age is kind of like this age. You can wave your hands and say they're kind of the same. So that's the detrital age. The detrital age is the stuff that's coming into Gale Crater, into the basin, from the surrounding basaltic highlands. So what we were hoping is that that's going to date the basaltic highlands around Gale Crater. Well, how well did we do? People looked at the surrounding basaltic highlands, that's what this is, and you can see these craters, and you can count those craters, and using a size frequency distribution appropriate for Mars, you can get a crater count age. And that's what these are. These are two different authors' crater count ages of the area around Gale Crater. They're much younger. They're significantly younger, 3.6 to 3.8. Now, I told you in the beginning that our crater counting curves are completely uncalibrated. We don't really know. We try. Again, I'm not going to disparage the people who try to do this. They have good reasons for the way that they make these. But we don't know for sure. We don't have it pinned down at Mars. So we don't know whether these crater counting ages are systematically younger than they should be, or whether this age is systematically older than it should be. We can't tell the difference. So both of these data points are real and true to the extent we can make them. There's obviously something that's different between them, and we don't know that right now. We've got to resolve that. How are we going to resolve that? I have the answer. The answer is the potassium-argon laser experiment, also called Carly. It's not Kale, and it's not Carl. It's Carly, like Carly Simon. So what we do is we use things that we already know how to do. I'm not an instrument tinkerer. I want the answer. I just want to get the science. So I'm using things that exist. I'm using LIBS, which is the ChemCam on Mars, on Curiosity. It does laser-induced breakdown spectroscopy. It means you shoot a laser down, you put a lot of energy on the surface of a rock, you ablate it, but you also excite those atoms. So you put them in an excited state, sometimes you ionize them, and then as they come down to a neutral state, they give off visible light. So you can look at it with a spectrum, break down that visible light, get the elemental composition. So we use LIBS for double duty. We get the potassium out of that, and we also ablate the sample, break all those bonds, and release all the argon that's in that spot that we just looked at for potassium. And then if we do that in a closed container, this is the only innovation in this whole scheme, is we do it in a vacuum chamber. And then you can collect that argon atom for atom, plumb it to a mass spectrometer, and now you have potassium and argon from the same spot on the same rock at the same time. We have to look at the volume of the pit we created because potassium, or because Libs is a relative measurement. It says 10% of your sample was potassium, but mass spectrometry is an atom by atom, so it's an absolute measurement. So to do that, we have to know how much material participated, and we look at the volume. But you can do that by using MOLI or the MI, any sort of microimager, and taking a stereo image and doing a tiny, tiny DEM. You get the volume that way. So this is all things that we use commonly. We use them on rovers. I don't need to develop them. All I need to do is develop how to use them in concert with each other. So that's what we've been doing for a couple years now. And in fact, this is something that's similar to some of the uranium-helium dating methods that are going on too, is you make a little pit and then you look at your noble gases that way. So it's not terribly innovative. I guess maybe that means I'm not that smart, but it seems like something that we can do in the near term with low risk. These are the kinds of ages we get. Now, I will put a disclaimer, these are bad. They are not good. This was all done on a manual system. Everything is a manual valve. Back in the day, every isotoper did this. Turn a manual valve, set a timer, wait 3 minutes, stare at the machine, turn another valve, wait 3 minutes. So we didn't do very many experiments, and so there's not a lot of data points here, and we didn't throw any of them away either. Ideally, what you do is make a huge number of data points, throw away the ones that don't fit your isochron, and get your isochron. So full disclosure, they're not many, and they're not that good, but they're not that bad either. So I know you can't see this. So we get, this is a 28 million year old Fish Canyon tuff. It's an Argonne standard. We get 21 million years. Here is Boulder Creek granite. So you can see it's very heterogeneous. It's 1.7 billion years and we get 1.6 billion years. So the idea is here is you just march across the rock. Every point has a different mineralogy underneath of it, and that gives you the spread in potassium that you need, and spread of potassium argon, and that's how you get your isochron. If you have a very homogeneous rock, you're going to get a data cloud, and that's not going to be that helpful unless your data cloud is small, then it's the age of the rock. So I can tell you, I don't have a slide that tells you how we are doing better, but we are doing much better. And my postdoc is just about to publish a really, really nice paper with really tight error bars. And so someday I'll get a slide made of that I'll show you a little bit better. Just super quickly, what we can use this for, the green diamonds here are ordinary chondrites. The red squares are Martian meteorites. The yellow circles are Martian rocks that we see with Curiosity and Spirit and Opportunity. And the blue diamonds are lunar rocks. On airless bodies, your mass spec has a better chance of measuring your sample gas because there's not a lot of other gas there. Things like Mars have a lot of sample gas that you have to pump away. So your level of detection is much higher. But even at Mars, all of these kinds of lithologies are accessible to you. For comparison, here's a sugartite. I'm not going to be able to date a sugartite with this method. So if you wanted to know the sugartite parent body or the sugartite parent flow in situ, I'm not your instrument. So you have to pick the questions that you want to answer that are going to be answerable by this method. All right, in the interest of time, I'm going to skip past, where we're going to go with this. Short answer is we're going to the moon because there's places you can take this on the moon. If you're interested about that, you can ask me. And just wrap up by saying, I am very amazed at the work that I do on tiny samples, tens of micron size samples, feeds into dynamical systems of the dynamical models of the entire solar system and extrasolar systems, and understanding how planets formed and evolved and moved. That is amazing to me. So working on this bombardment history has brought together sample people, dynamics people, exobiology, habitability, formation of life on Earth. It brings together all those disciplines in a way that just astonishes me, and I'm very lucky to work in this field. And so, yeah, and then I'll just put in one last plug. Come test your hypotheses with me. Thanks.
I'm sure there's tons of questions. You just want to grab them from the audience?
Yeah, sure. Just shout them out.
I was just wondering, what case at Mars, so you get sandy, is that a common mineral in Mars? Isn't that normally found in things like more evolved rocks, more dusted rocks? Where is that?
It's unusual, right? We also see tritomite.
What is
It's a high temperature polymorphic quartz. So we were speculating that there's a high temperature volcanic region nearby, but we don't know. I don't think anyone knows how that really works. It's a mystery. Yeah, well, so the surface of Mars is more alkali-rich than we expected it to be. Just based on the sugartites, you'd expect it to be pretty depleted in volatile elements. And since we've been there with the rovers, either all of our rovers are systematically uncalibrated, which is hard to believe, or there's a lot of alkalis. Our feldspars are high in alkalis. It's interesting. So it's more volatile rich than we thought it would be at the surface. So there's plenty of potassic rocks that Carly could look at.
But there's not quartz.
There's tritomite.
I said there's not quartz.
No, not yet.
On your map of the moon, there were also those lunar Russian missions that landed on the surface. I remember some of them, and I don't know which one, also returned some samples.
Yes.
Do you have access to those? Because they look further from the three terrains than the Apollo samples.
I did. I published a paper on some of those lunar samples. They're mostly basalts. They picked up mostly basalts. They were on basaltic plains. I ended up dating things that ended up being agglutinates because we thought, oh, well, maybe these are impact melts, but they're not. They're full of terrestrial air. So we haven't found... another one we thought was Crisium impact melt. So Tim Swindle did date some of that and argue that it might be Crisium impact melt. Sometimes it's hard to distinguish whether it's a basalt from whether it's an impact melt. So some of them are hard to determine. So there is a little bit of work on that, but it doesn't change the overall story. And Katie Joy just gave a talk at Meteorological Society pleading with anyone who knew how to get their hands on those samples, and they are not giving them out.
So it seems to me your best bet for getting good sampling is to go to like the meteorite data set, right? For this probability distribution of when you see the different ages. And those are mostly coming from the Antarctic search for meteorites. So how often do you get a lunar? How often do you get a Martian compared to how often do you get?
Wow, that is a great question. And if I were Ralph Harvey, I could answer you, but I don't know. I know that the majority of lunar samples coming out are from the hot deserts, not from Antarctica. There's a lot of them coming from hot deserts, and a lot of them are paired. So there's the same stone, just picking up different pieces of it. But we have, I mean, one of the reasons that we keep going to Antarctica is to get more Martians and lunars in our collection. So it happens. We found a lunar every time I've been. So I've been 3 times, and each time we found a lunar. One of the years that I went, the other team found a Martian.
So it's like 1 out of 500, 1 out of 1,000, something like that.
Oh, it's more. It's less than that. Just ordinary chondroids overwhelm you. Yeah.
That's the cheapest sample return, right?
That's what Ralph would say. It's the cheapest sample return there is. Yeah.
And you reconstruct the histograms of time on the meteorites and otherwise, it looks like there's actually a fair interval of time that is represented by
Yes.
What is the significance of that, or is there any significance of that? I mean, because it's not a single discrete peak.
Right.
It's something that's attracted from flat.
So we think that probably it's related to if you did have a different population of velocity of impactors, that tails off with time. And so you have fewer and fewer with time. And also you have smaller and smaller ones with time. And so the meteorites, I think, are collecting more of the smaller impact sizes, just because they're at the surface and these clasts that we're looking at are so small. these class-choked impact melts are very common even in smaller impact craters. So when you get a nice chunk of impact melt that's this big and it's uniform throughout, you could argue that comes from a very big basin and you're only dating the big basins. When you get these small class-choked things, they could come from much smaller craters, which can happen longer in any sort of tail off of a distribution. You do all your big stuff up front, and then you have smaller and less frequent impacts as they go on. And you can still be creating meteorites in those.
Okay, but it doesn't peak and then tail off so much, does it?
The meteorite data doesn't show that, but we're speculating that the event that makes those meteorite data did. And it's just a thresholding effect.
So I want to talk about your Carly instrument. And I've seen some of your data presented before, but since the uncertainty hinges on estimating the volume of how much sample you've removed, I'm curious how many variables you've explored, because your architecture centers on powdered samples. Right?
Solid samples.
Well,
The inverse of that.
in your envisioned implementation on another planet, you would presumably look at powdered samples.
No, so the powdered samples on Curiosity, that's our worst situation, because when you libs a pile of powder, it goes.
That's kind of what I'm getting at.
Right, yeah. So we do solid samples. So you can do that either by having a core, a solid core that you could envision on Mars, or on the moon. What you would do is scoop and sieve the regolith, get pebbles out of the regolith, and
So
use
individual
pebbles.
pebbles.
Individual pebbles, yeah. The moon is great because it does all the work for you. It breaks up the bedrock, so you don't have to bring something to break up the bedrock. And it leaves it there in a pile for you. And then you scoop it up and sieve it. It's like panning for gold. So the majority of the regolith that you're going through is developed off of the substrate that you're interested in. You do get foreign contributions, but we know lunar rocks, I think, well enough to argue that when you do libs, you get the complete elemental composition, and you would be able to say, this is a creepy rock, this is a Mare basalt, this is a Highlands rock. They're different enough from each other that a simple elemental assay will tell you that. But that's probably not your question.
I mean, you're getting closer to it, because I already know it's not a powder.
Yeah.
But you'd have to locate that directly underneath your beam. I don't know what the beam width is. But I guess you've looked at different pebble topographies and verified your estimated volume versus mass loss. I guess afterwards in the lab you can do a mass loss comparison.
Well, we don't do a mass loss comparison. What we do is a laser scanning microscope, which gives you very, very high resolution volume. And then we compare that with what you would get with a camera. But then you have to calibrate that system out. So there is mass loss that doesn't participate in the experiment. When you hit it with the laser, you can ping pieces off that then didn't participate in the experiment. And they contribute to volume growth, but not to argon. So you have to calibrate that process out. So we don't control it, we just try to understand it. Does that make sense?
Maybe one more question. Jessica,
So, Barbara, I may have missed something, but I think you said your meteorite, Darko, whatever it was, that you think came from South Palladium was 3.5 billion years old?
Yeah.
Isn't that kind of young?
It's not South Palladium Basin. It comes from the South Palladium
But
Basin.
you're not saying it is South Palladium?
I'm not saying it is the South Palladium impact. It's a younger impact.
Ah, okay, I missed that.
And that's part of the story that we would get with an SPA sample return mission, is we would be looking our best for that SPA age, but we would also get a range of ages younger from all the subsequent impacts in that terrain, and that would be one of them. So that may be Apollo or Jenny or just a small unnamed impact, Bose, Baba, who knows?
Okay, well, it seems like there's a lot of conversation. Let's thank Barbara one more time. If you still have any burning questions, please come up to the Geology Lounge on the